This is a weekly summary of interesting news that is relevant for my lectures at the Eastern Switzerland University of Applied Sciences. My name is Thomas Bocek, and today we will discuss 5 topics, including the Cloudflare outage. The first topic, it's this one here. In the application architecture and distributed systems lecture, I talk about scaling, and here we have some numbers, what scaling actually means. Google ran a 130,000 node Kubernetes cluster in an experimental mode, doubling its previous supported limit of 65,000 nodes due to scaling demand of AI workloads they mentioned. And this shows horizontal scaling in practice. Adding more nodes creates new bottlenecks in the control plane that require solving problems like caching, distributed storage, and efficient scaling algorithms, which we did not fully cover in our lectures yet. The tests sustained 1,000 pod operations per second, and this means the system was processing 1,000 new pod requests per second, while at the same time assigning 1,000 pods to nodes per second. And this throughput matters when companies need to respond to events. If a service suddenly becomes popular and needs to scale from a few hundred pods to 50,000 pods to handle demand, doing this in under a minute instead of 10 minutes makes a difference. In their tests, 39,000 pods were preempted in 93 seconds, which means at the same time deleting low priority nodes and creating new high priority ones. And another test scaled a cluster to 130,000 pods in 3 minutes and 40 seconds. They also mentioned that power constraints are becoming the limiting factor. If the pods have, for example, an NVIDIA GPU that requires 2 to 3 watts, meaning that a 100,000 node cluster could need hundreds of megawatts. And according to the article, there were some key architectural changes for this kind of scaling. So the API server, they used a consistent read from cache feature, reducing database load by serving requests from memory. And Google uses a proprietary spanner-based key value store, distributed database that spans multiple data centers and can handle 13,000 queries per second. For example, for lease updates, those are periodic heartbeats proving each node is still alive and healthy. And for job management, they use Queue. Queue provides batch system capabilities with all or nothing scheduling, ensuring all pods of a job start together or none at all, and fair sharing policies that distribute resources fairly among competing workloads. And while Google anticipate demand stabilizing around 100,000 nodes, the 130,000 node test isn't officially supported yet. And what I also found interesting here, they mentioned that they have customers operating in the ranges of 20 to 65,000 nodes. The next article, it's the following article here. This article is about event sourcing, a topic that we also discussed in the application lecture. And the core idea is that event sourcing stores state changes as a sequence of immutable events rather than overwriting data. Instead of storing just the current account balance, the system records every deposit and withdrawal. Current state is calculated by replaying all events. And this architecture solves specific distributed systems problem. The append-only nature makes writes fast. There are no updates, no deletes, just inserts. And the author mentions in this article that they processed 10,000 events per second using a PostgreSQL server. The author provides working code examples in Go for the event store, including schema design and concurrency control. Event sourcing is commonly combined with CQRS, which stands for Command Query Responsibility Segregation, that separates write operations from read operations. Commands modify state and generate events. Queries read from optimized projections built from those events. These separations allow each side to scale independently. And the challenge is that projections update asynchronously, creating eventual consistency between write and read models. Query may return stale data until projections catch up, which is typically within milliseconds or seconds. The next snapshots, they are essential for performance with large event stream. Rather than replaying thousands or millions of events every time, the system periodically saves snapshots and only replays events after the snapshot. For distributed transactions, the Saga pattern coordinates multi-step processes across aggregation with compensation logic to handle failure. If money transfer stops somewhere in the middle of a transaction, then compensating events can reverse earlier steps. And also quite interesting here, the lessons learned. The trade-offs are clear. Storage costs increase 3 to 5 times due to storing events, projections, and snapshots. The mental model also needs a shift, but for financial systems requiring complete audit trails or systems needing time travel debugging, the benefits may outweigh the costs. The next topic is about an expensive mistake. It's the following article here. It's not the Cloudflare level expensive mistake, which we will cover later on. It's an article about unexpected cloud costs from routing misconfiguration. The company transferred 20 terabytes of data from an EC2 to an S3 instance in a single day, expecting it to be free since both services were in the same AWS region. Instead, they received a bill for over $1,000. And the problem when using VPCs with NAT gateways, S3 traffic routes through the NAT gateway by default, even for same region AWS services. And NAT gateways, they charge 4.5 cents per gigabyte for all data processing, regardless of source or destination. And at 20 terabytes per day, this adds up to approximately $900. And the author had researched cost beforehand and confirmed that EC2 to S3 transfer within the same region are free. This is technically true for the data transfer itself, but doesn't account for NAT gateways processing charges. The traffic was routed out through the NAT gateway and back in, incurring processing charges. And the solution is VPC gateway endpoints for S3, which creates a direct route from the VPC to S3, bypassing the NAT gateway entirely. Gateway endpoints for S3 are completely free, no hourly charges. And the fix required adding a single Terraform resource to create the endpoint and associate it with a root table. And what surprised me is that 20 terabyte through a NAT gateway costs $900. For comparison, my 25 gigabyte per second init 7 connection costs roughly 65 Swiss francs, which is around $70 per month. So this is less than $3 per day. And if I can fully saturate, probably I cannot, but if I can fully saturate this connection for 24 hours and the NAT would be externally reachable somehow, which I know it's not, but if we could somehow create a tunnel into this private subnet, then I could push approximately 270 terabytes of traffic to an AWS customer's NAT gateway. and this would cost me $3, but generate a bill of over $12,000 for the victim, an amplification factor of 4,000. But only if I can reach the private subnet from outside where I should not have access, and also if I can saturate the 25 gigabits per second across the internet from a residential connection, and I expect some countermeasures from Init7 blocking me or at least contacting me due to this high unusual traffic. In any case, I think this is an interesting view on cloud costs. The next article is again about Kubernetes. It's the following here. The author describes how Kubernetes can function as a private cloud running on hardware you control rather than public cloud providers. The argument is that Kubernetes provides the same capabilities as public cloud services, elastic compute, storage, databases, and AI workloads, but without vendor lock-in or unpredicted costs. Bare metal Kubernetes can deploy directly on physical servers without virtualization, eliminating hypervisor overhead. And this provides better performance and resource utilization, particularly for AI and high performance workloads. And this research here, they showed 1 in 5 Kubernetes cluster already deployed to bare metal, and they could observe a resource utilization improvement of up to 20%. And the motivation is cost control and autonomy. Public cloud bills can be unpredictable, and in the previous article we saw what can happen with a misconfiguration. With bare metal, cost becomes predictable. You have servers, you have racks, you have power that you need to pay. You control data location for compliance, avoid silent replication to third-party regions, and aren't blocked by providers' API limit. The tooling has also matured. Infrastructure as code and GitOps handle cluster deployment. Kubernetes operators automate database management, queues, and observability without manual intervention. And tools like Rook, for example, provide distributed storage similar to Cloud Object Storage. And Cloud Native PG delivers managed PostgreSQL with automated failover. The trade-off is operational complexity. You must handle cluster setup, high availability control planes, storage replication, and hardware maintenance yourself. And the author argues that it isn't eliminating public cloud, but commoditizing it. You can still burst workloads to cloud providers when needed, but your default infrastructure is under your control. For organizations hitting cost limits or needing data sovereignty, treating Kubernetes as a private cloud platform offers an alternative to full public cloud dependence. And in my home lab, I do not have workloads that require scaling, so I did not yet deep dive into the complexity of Kubernetes. Now, the last article is about the Cloudflare outage. This was huge. Last week, Cloudflare experienced a major outage lasting several hours that affected approximately 20% of websites globally. The incident took down major platforms, including Twitter, Discord, ChatGPT, and many other services. And the outage was triggered by a database configuration change that caused a feature file for Cloudflare's bot management system to double in size. And this resulted in the bot management feature file containing more than 200 features, exceeding the pre-allocated memory limit for these 200. And this caused the system to panic and return 500 errors. And this file was then distributed to all machines across Cloudflare's network, and the software reading this file had a size limit below the new size, causing it to fail, and the file was being generated every 5 minutes, leading to intermittent failures, as sometimes good and sometimes bad configuration files were distributed across the network. And the issue was resolved by stopping the generation of the bad configuration file and manually inserting a known good file into the distribution system. Service was largely restored after 3 hours, with full restoration taking approximately 6 hours. And the outage affected core CDN services, and many users couldn't access the Cloudflare dashboard to modify their DNS settings to bypass the proxy, showing a dependency problem. Some comments expressed worry about how much the internet depends on a single provider. When Cloudflare goes down, approximately 20% of website becomes unavailable. And this centralization was compared to similar dependencies like AWS or Azure, which also experienced major outage recently. And some noted the irony that the internet was originally designed for decentralization to survive failures, but economic forces have pushed towards centralization. Some comments pointed out that businesses often prefer using major providers like Cloudflare because when everyone goes down together, it's easier to explain than being the only one down. This creates an incentive where companies don't invest in redundancy or alternative providers. The phrase "nobody gets fired for buying Cloudflare" appeared in several variations. And a common frustration was that Cloudflare's status page took 15 to 20 minutes to reflect the outage, initially showing everything as operational. And this reflects a broader industry problem where status pages are manually updated rather than automated, often for political or SLA reasons. Also, both the recent AWS and Cloudflare outages share similarities as human-triggered configuration errors, but differ in their technical nature and impact patterns. Both show the difficulty of managing distributed systems at scale, where changes in one component can have unexpected global effects. That's it from my side. This time, no crypto news. This gives the crypto market time to recover. See you next week.